Hello, RubyConf. I'm so glad to have this opportunity to present to you. Today, I'm going to talk about golf scripting with Ruby and how I help Santa to schedule Christmas. I hope you all enjoy my talk. A little bit about me. I'm a technology fan that has been working in the technology world for more than 20 years in different capacities as system administrator, developer, tech lead, engineering manager, and project manager. Right now, I'm working at Smile, helping build the loyalty layer for the internet. If you're interested, we're always hiring Ruby developers. You all know Santa, right? I know that many of you are not yet thinking about Christmas. However, a project that big is not planned in just one day. In fact, right now at the North Pole, they are in the final phase of gift production, and they're almost done with scheduling their delivery. Despite what you see in movies, it's not Santa himself who delivers the present. He gets help from the elves. As you well know, good kids get presents, and naughty kids get coal. Now, I've worked in automated elections for a long time, and as in elections, Christmas is a project that you plan for a long time, but have to execute without failure in just one day. Maybe my experience is the reason why Santa asked for my help with the problem he has. For reasons that I am not at liberty to share, even in North Pole they have NDAs, the elves do not spend time traveling between Santa's sleigh and houses, nor does his sleigh spend time moving from house to house. It takes two elves 4 seconds to deliver each present, and because coal is heavier and more dangerous to handle, three elves spend 5 seconds to delivering each lump of coal. Presents have to be delivered to one house at a time, and elves must go back to the sleigh and collect the next gift before going to the next house. We leave no elf behind is the motto of the Elves Corps. So that's the situation, and Santa needed help with an algorithm to help him determine the least amount of time that a fixed number of elves can take delivering presents, given a map of houses with the number of naughty and good kids on each one. Again, for reasons I can't disclose, the code has to be written in a very peculiar way in order to be able to run in Santa's quantum mainframes. But let's say this Santa's quantum computers need very short fragments of code to run efficiently, instead of what we usually know as efficient code. They need to be written using golf scripting. And when I mention golf, this might be what you all be thinking. But no, it's not that class of golf. It looks more like this sitting in front of a computer, figuring out a problem like we do every day, or at least most of you probably. Now, what is golf scripting? It's basically a type of puzzle programming competition with the goal of implementing an algorithm in the shortest possible source code. As for the problem we are trying to solve, let's call it the scheduling problem. Let's take a look at it. Let's look at a first example. We have a house where we have to deliver one lump of coal and one present, and we have three elves. Now, I'm a visual guy, so I'm going to make a chart to see how long it takes to deliver the present and coal. It takes three elves 5 seconds to deliver the call, and two elves 4 seconds to deliver the present. So the last amount of time is going to be 9 seconds. Let's try with an example a little bit more elaborate. We have a house where we have to deliver four presents and one lump of coal. There is always a black sheep in the family, right? And we have five elves to perform this task. How will our chart look? We deliver a present, then coal, and then the rest of the present. No matter how we rearrange the order of delivery, the less amount of time it will take us is going to be 12 seconds. It could take us more, depending on if we do it in a different order, but it's never going to take us less than 12 seconds. Well, it turns out that this problem is a well-studied problem in computer science, and it's called a bin packing problem. In our case, it is specifically related to orthogonal packing in two dimensions, which refers to problems of packing an arbitrary collection of rectangular pieces into an open-ended rectangular bin so as to minimize the height achieved by any piece. For Santa, L represents the list of blocks, which are determined by the number of naughty kids and good kids in the house, and the time it takes the elves to do it. And when the paper talks about minimizing the height, the equivalent is minimizing the time it takes to deliver the presents. And the constraints are the same as in our problem. It needs to be disjoint, as in an elf cannot be delivering both a present and call at the same time, and also orthogonal and oriented, as we can't rotate the blocks. It takes 2 elves 4 seconds to deliver a present, but that doesn't mean that we can use 4 elves to take 2 seconds. Now, the funny thing is that when I got to this part, the only thing I could read was NP complete. And in my mind, that was just hard. Luckily for me, later on, they offer some light at the end of the tunnel. Thank God for academics. What would we do without them? So, no matter how much they know, they haven't yet figured out how to write for normal humans. Anyway, now we have our problem clear. It's a two-dimensional bin packing problem that can be solved using a button-up left justified algorithm. Now, I solved the problem using normal Ruby code, and I'm going to show you how to solve it. Now let's solve. Here we have the complete solution for Santa's problem. This code is around 4 kilobytes, and by the end of this session, we are going to reduce it to 400 bytes. Now, to the left of the screen, we have two things. The result of the test running for this test, and also the script size. Anytime I save the file, that will be updated. So you will notice if I mess it up. Now, the first thing I do when trying to golf some code is look for pieces of code that are optimizing it, but that could be replaced by brute force implementations. In our case, here, we have these unique permutations for an array method, which is adapted from an algorithm by Professor Donald Knuth. This method is incredibly elegant. It might not be idiomatic Ruby, but you can see the brilliance of Professor Knuth all through it. Anyway, it is still 25 lines long, and because we are focusing on reducing the code size and not its efficiency, we can change it completely by the built-in array permutation method. So let's do that. Granted, we will get all permutations and not just the unique ones, and that will add a few cycles, but that's not our aim. Now, if we have method here, like this bin pack max height method that we are calling only once, we can get rid of them method calling and the method definition by inlining them. Now, in our case, this added 100 bytes to the script size, but that is because indentation. And if we were using tabs, it would have been half of it. But we're going to deal with the spaces later. So now I'm going to make it up for adding all of those indented lines. And I'm going to remove the empty lines and all the comments. Who needs comments anyway? This is kind of one of the easiest way to reduce the file size. So let's get rid of empty lines. Under virus return. And whoops. Now let's get rid of all the comments. So this is comment any characters till the end of the line and encourage return. So let's try again. We start the line, we have spaces, we have font sign for the inner characters, any times at the end of the line for the first return. There it is. Oops. And we're already down to almost 2 kilobytes. Now, if I were a politician, 50% of progress on my promise will put me on the top 1%. But let's keep moving. I can also rename all the variables in our code to use only one character names. This will definitely save me a lot of bytes, but it's not as easy as it sounds. It's actually a lot of work if you have many variables and don't want any scope collision with the names. this can sometimes take a lot of time. So that's why through the magic of Git, I'm going to check out my code directly to that step. Changing everything to one letter variable names lets me see that in some parts of the code, the non-semantic variable names forces us to split our code across multiple lines. But these lines were actually just one statement, or multiple statements but could be shortened to just one line. So I can save some bytes by removing those unnecessary character returns, which will also have the added benefit of being able to fit more code in the screen so you all can see it better. This was one statement, as it is this one, and this also can fit in one line. And looking at the code as it is, we can also notice that there are a few variables that are only used to store intermediate results. For example, age here on line 2, which is only used here on line 3. So we can get rid of it. But we also have B, which is only used to calculate O, which is only used to calculate F, which is only used to calculate a minimum. So we can get rid of all of them if we just change the calls. Now, J here can also be removed. If we look at what this code is doing, it's remapping it to use the size of our blocks instead of the zeros and ones in the array in which the permutations were created. And if we use directly the size of the blocks when creating the permutations, we can get rid of this mapping here. Now, we also have D here, A here, which is only used to calculate D, so we can get rid of the intermediate A. One of the other things I can do is change all of the do end blocks by opening and closing brackets. Do end are 5 bytes, and an opening and closing bracket are only 2 bytes. So let's do that. Do by an opening bracket and end by a closing bracket. Now I also changed the end for the method definition, but I can also get rid of the method definition if I change it by a lambda, especially using stubby lambda syntax. Who needs names for the functions, right? I'm almost running of easy optimizations and quick gains. But looking at the code here, we can see that R and L both are calculated iterating over C. And I can probably save a few bytes if I merge both iterations into one. The caveat here is that I will need to return a pair of values from the block and use that instead. But I'm pretty sure this is going to reduce the size of the code. Well, this talk is recorded, so I'm 100% sure. So let's do that. Let's move this line here. I will need a different variable to increment here. Let's initialize it here. And I will have to return A and B, but I can get rid of this. And whenever I'm using R, as in here, I will use the first of my pair of values. And whenever I was using L, I will have to change it to R and use the second of my pair of values. Now, we can say that in general, the Ruby standard library method names are terse and succinct. They don't tend to be long names. There are always some exceptions, of course, and I'm looking at you, verified transient heap internal consistency. However, the longest Ruby method here in this code are permutation with index and reverse. There is no shorter alternative to permutation, and on itself, using it is saving us a bunch of bytes. However, there is something that I can probably do about the other two. Let's start with index. That's a whopping 10 bytes. What a waste. And that isn't even counting that we have to add an additional argument for the index in the blocks. There are so many bytes on it that we can save characters by not using it and incrementing a counter ourselves. I use it twice here, so I can save an additional byte by creating and initializing both counters at the same time. So let's do that. And also get of this one. That helps me manually increment here. And in this case, I can get rid of each with index. I love all of this. I have to use the second counter variable and manually increment it here. Now, the other long Ruby standard library long name method that we are using here is reverse. You will have to trust me on this one, but I can change it by, well, you don't have to trust me. You can see the test passing, but I can change it by this. Now, because I'm incrementing I here, I can probably also use that to get rid of this one. Now on lines 4 and 5, I'm assigning 0 as the default value to n and g, in case they are not assigned on line 3. I can save a few bytes if I assign those defaults directly from the map string by leveraging the fact that assigning variables from an array discards the excess values. And on line 5, I'm calling next, but the same result can be achieved if a default value of 0 is returned from the following block. So let's do that. Now, I'm in the business of altering loops. I can also take a look at this in line 12 and 13. And instead of breaking, do nothing, or nil, which is as close to doing nothing as you get in Ruby, or p, which when called without arguments also returns nil. Now be careful when doing this. You cannot remove all of your breaks, but it just happened to work for this particular algorithm. I can also replay all instances of each with map and save 1 byte each time. Or should I say map time? Both of them are iterators. And if not using the result, they are completely equivalent. Except for those picky code reviewers, of course, which I hope you ain't. But let's do that. Each by map. There it is. 3 less bytes. And on line 3, we have one character string. And I can save 1 byte by using this little known Ruby syntax for 1 character strings. And on line 23, on line 21, we can get rid of these parentheses by using a little bit of algebra and changing the sign here. Now, I've been promising I'll deal with all of those white spaces. And no, this doesn't involve any tabs, but it's time to finally do it. Who needs white spaces anyway? Let's get rid of all of them. Well, turns out that we do need some white spaces to avoid confusing the parser. We have to add a space here in our ternary operator, and also what is gfx? I don't know, and the parser won't either, so we'll do this. But that wasn't so bad. We only needed 4 white spaces, after all. It turns out that we also don't need, in some cases, new lines. Every block, including pipes, can be joined with the next line. And we also don't need to keep blocks ends by themselves. So let's join lines 1, 2, and 3. Lines 3 and 4 here. Lines 4 and 5. Lines 6 and 7. Lines 9 and 10, a block end. Lines 10 and 11. Lines 12 and 13, a block end again. Lines 15 and 16, block end, and then all of these block ends be joined in one line. Now, this is as far as I can get, 392 bytes. This is even better than the 400 bytes I promised at the beginning. And the truth is that every time I prepare this talk, I manage to shave off a few additional bytes. Maybe if you try it, you can probably improve my solution. But I still have some work to do. The convention in the code golfing community is to present this as a one-liner. So let's replace all of the new lines by semicolons, and the code will still be the same, but will look more condensed. So this is it, the final result. Now I'm really feeling like Tiger Woods, all in one line. And now a warning from the North Pole Surgeon General. Golf scripting is an addictive obsession, where you spend a lot of time solving problems and generally the code you produce is useless for anything else. However, it's also a fun and challenging way to learn to solve problems under artificial constraints and to practice out of the box thinking. Just to be clear, this is intended to be fun and it's not something I will do in any code base at work and much less suggest you do it. But I have given this talk before and I have gotten mentions on Twitter that it was full of bad practices. Well, duh, of course. And you're free to tweet what you like, but come on. Let's see some tips for golfing in Ruby. Some of them we already saw during the golfing exercise, like the one character string, where we could use the question mark preceding the character and save one byte, or using nil, which by itself is 3 bytes, but we can always call p without arguments and it will return nil. Some of them we didn't see, like true, but can be derived from previous ones, like true is 4 bytes, but if we negate nil, we also get true, or we negated p and it's only 2 bytes, and we achieve the same results. And what about false? Well, false is 5 bytes, but if we negate 0, we get the same. Like we could also double negate p, but that will be 3 bytes, but if we negate 0, we only get it in 2 bytes. And using a string interpolation is in some cases better than, for example, calling 2else. If we do the same to an interpolation, we are saving 2 bytes. And this even works when doing interpolation instead of concatenation. We can save 1 byte if we interpolate instead. This is because we don't have the opening and closing brackets and the plus signs surrounding. In case we are dealing with big numbers, specifically multiples of 10, we can use scientific notation to save at least 1 byte, or 2 or 3, depending on how long the number is. Granted, it will give you a float, but you can normally substitute it safely. Let's talk about operator methods. In some cases, we are forced to use parentheses because of operator precedence. But we can also use operator method to get rid of those parentheses, because the precedence calling the method will be evaluated first. And what about initializing arrays? We normally do this if it is one value, but we can also do it this way and save 1 byte. And what about arrays with multiple values? Well, I bet you didn't know that we could also do it without using the brackets, and it will be the same. And when we call compact on an array, we are removing the nil values from it, but it's a 7 bytes method on an array, and you could achieve the same result if we subtract an array containing only nil, and if we use p, that's 4 bytes less. And if we want to remove duplicates, we usually call unique. Well, unique is not that long, it's 4 bytes, but we can even make it shorter if we intersect an array with itself, specifically if we are using one character variable names. So these were a few tips about golfing in Ruby. I bet there are more, and you can find them yourself. Finally, this talk would have been possible without the amazing code golfing community at Stack Exchange. Specifically, I'm sharing here the links to the Jotmos problem on which this talk is based and to their excellent tips on golfing in Ruby. But if you want more problems to golf, you can go to the Stack Exchange Code Golfing community. If you want to take a closer look at my solution, I'm also sharing the repo for my code. It includes Git tags with every step of the process. And if you don't mind the boring language in papers, there you have the link too. Thank you all for your attention. It was really a pleasure for me to be able to present here in RubyConf 2021, and I hope to see you all next year.